In order for us to find the resultant, I want you to take this law down. It's called parallelogram law. Right? So we're going to use parallelogram law to find the resultant, right, of forces like this that have an angle between them. All right? So head of parallelogram law. Right? Parallelogram law is a technique used. Parallelogram law is a technique used to find the resultant. Parallelogram law is a technique used to find the resultant of forces acting on an object Parallelogram law is a technique used to find the resultant of forces acting on an object by using a scaled diagram. By using a scaled diagram. By using a scaled diagram. Right? And I'll give you the steps. The steps to parallelogram law. Number one, the first thing that you're going to do is you're going to come with an appropriate scale, right? So you're going to use an appropriate scale. Right? Use an appropriate scale. Step two, you're going to construct a parallelogram. You're going to construct a parallelogram, right, using the dimensions given. Right, so you're going to use appropriate scales, construct a parallelogram using the dimensions given. Then you're going to draw a diagonal. Right, you're going to draw a diagonal and read off the dimensions to find resultant force. All right, it's here for you, right? And I'm going to show you how to do everything using that example there. Right, so we're going to use our appropriate scale, construct a parallelogram using the dimensions given, draw a diagonal, and read off the dimensions to find the resultant force. Okay, real simple, but again, it's a scale diagram, so you're going to have to be exact with your value, right? Ready? So we're going to use a scale. Of course, the scale I picked has to do with. Yeah, where we go. Right? The scale I pick is basically going to be based on what you put in your notebook, right? So for this one, 6 and 8, we could use a simple scale. We could use 1 centimeter is equal to 1 Newton, right? So 8 newtons is how much centimeters? 8, right? And 6 newtons will be. So suppose it was 80 newtons. Will this scale work? No. Right? So you had to use a larger amount of newtons per centimeter. Okay? And what's the angle between them? What's the angle between them here? 90 degrees. All right? So you're using your protractor to get that angle. All right? So watch it here. I'm going to show you what to do. Watch up here first, right? Ready? Watch here first. First thing first, you draw your 8 centimeter line. Right? It has to be exact, right, Tolia? Right? Using this scale, draw a line 8 centimeters. Then using a protractor, place the middle here and read off, and read off 90 degrees. Right? When you read off where 90 is, go up 6 centimeters. There should be 6 centimeters. Right? When it completed, when it completed, you want to complete parallelogram. Parallelogram simply means these two lines parallel, these two lines parallel. Right? So I'm going to draw a line on top here, parallel to this equal line. Right? Then the remaining should be parallel to this and equal as well. Okay? That's a parallelogram. Right? So we did step 1, we constructed the parallelogram. Step 2, last step is to find the resultant force. Right? If I have a force acting upwards here and to the right, we know that the resultant is here. That's okay? Everybody okay with that? So you draw your resultant now. Right? That is your resultant force. To complete this, all we have to do is to find the length of this line, which should be a particular value, and then use the scale to convert the value to newtons. 1 to 1. So if we get 20 here, this should also be 20. That's okay? Take your time, right? Draw your lines, measure your angle, construct a parallelogram. Go ahead. Right, for those that look for the tractor, you can probably average 90, but you can't do it for the others, right? You can probably average 90, but you wouldn't be able to do that for the other with an angle. All right, so this brings us to the end of resolving, and this parallelogram law will also work for anything. It doesn't have to be forces. It could be two winds blowing different directions. All right, any factor, and you want to find the resultant, you can use parallelogram law. Okay. Oh yeah, work it out then. Some more you got. But I got one view. Great. Right, measure it and then tell us what you get for your tell me what you get for your diagonal. W lux. Then you go right. Measure it properly, right? Measure feet and measure 6. Then tell me what you get here. But I'm not going to get out. Anybody else? Okay. Anybody else got it? Online, somewhere again, please. Come up, what values they got? Then I'll put it diagonal. Online, send your answers now, please. What you got? Right, it's two lines that have made of the parallelogram broken lines, right? So we check out online. Celine, check it back again. You're a little off there. Narissa, well done. Rajiv, well done. Yeah. Huh? Yeah, 2 arrows. 2 arrows mean resultant. Right? 2 arrows mean resultant. Good job, Rajiv, Narissa. Arissa, what you got? Cupid, Jilan, what y'all got? Correct, Arissa. Arissa, you're doing your work here. All right, let's go again. Right, so for those who did it properly, you should get 10 centimeters. So the answer is 10 newtons. All right. Yeah. I want to change it slightly with example 2. I'll still keep it at 90. Right, but I put in 1 here and I put in 1 here. So anyway, I tell that up. Tell me what's a good scale that we can use here, right? What's a good scale we could use? Here's 50 newtons, and here is 130 newtons. Sorry, 120. Before you tell me, pick on somebody. Nathan, where is the resultant force here? Here. Where is the resultant force of these two objects? That come exactly where the joint. Here. Here is east and here is south. So that one here, southeast. Okay, right. So it'll give you an idea of where to put your resultant, right? So looking for a good scale to use here. What's a good scale? Eton. What's a good? Of course, I can't put 1 is 1, right? 1 centimeter is 1 newton. 10? Okay. So Ethan said 1 centimeter, 10 newtons. Not good. Do. Anything else to do? One is what? Yeah, one is 10 looking like the nicest. Okay. Take your time, construct the diagram, find your result on force. Okay. Again, I'll leave in this this example as 90 degrees, right? Online, you're getting through. And again, answer some people at K-Sharp, J-Lab, experience that my answer. Right, next week Friday, right? I know it might be I think you all might have school, right? But I have lessons like normal, right? If you want to stay online, you can stay online, right? But I have lessons like normal next week. Okay. Next week they have right, but lessons like normal, right? But I'm going to have lessons 1 week. I think that would be good to do well. Because in a week I won't have lessons. But I will be minded because I'm now closer. Right. Keep on your last one. Right. Maria, Dominic here, Gerard will send me other message, Gerard Manawi. Gerard will send me nothing, boy. No, next week is normal lessons, right? Normal lessons. Where is Gerard? Gerard was here a little while ago. Gerard gone. Right, Gerard. Misspeak there. We are not there anymore. Very cheap. Sorry now. Done Java. And done in Java. Demari. Demari. Marinaya. Lakshmi. Lorena. Annalie, Faro, Salario. Salario again, too? How much again? Huh? We're online. Kavish, you getting through? Sunny answer. Elijah. Pedro, then set my thing, Isaac, Amari. Online, send your values, correct, Rajiv. That's close. Keep it as good, but remember to convert it, right? Never said that's good. Kavish, check back yours. Keep it correct. Robin. Nathaniel, Abdul. The one next, Nathaniel, I don't need. Name again? Nathan. Oh, okay, okay. Nathan. It'll take my little while over there. Chavi. I'm just Chavi and Fishish. All right. Fine. Yeah, you have to say. So, Rahim. And the chance to finish on this thing here. Where Rahim? Alex is Alex boy. Maybe can't right? Anybody did not hear the name? Or name? Right, didn't get your name. Just come back to name again. Yeah. All right, so let's see what we got. I'm just gonna change it one more and then we're moving on to something new, right? Still on forces. Right, so 1 centimeter 10, so you draw a diagram. That's 5 centimeters. Right, and then you draw your next one 12 centimeters. Right? Right? And then you measure your angle 90 degrees. That's okay? You measure your angle 90 degrees and then you complete the parallelogram. Here you have to be careful, right? From here, just make sure you measure back the same length. If you do it properly, then this automatically becomes the same as this. Okay? And then come down here. That's the resultant force. If you do it properly, your resultant force is 13 centimeters. 1 centimeter 10. So 13 centimeters is 13 multiplied by 10 newtons, which is 130 newtons. You okay with that? Nice. I'm going to change it slightly. All I'm going to do now is just change the angle in the middle. All right? And that's it. Right? That'll be it for results. All right? So I'm just going to change it slightly. I'm going to give you one with a weird angle, but sometimes you can do like 60. For those who don't have a protractor, oh wait, you're going to do construction in maths here. Yeah, make it construction and maths. I'll be just taking the lead. Yeah, lose mark pretty soon. Right, last one, last one. You have an object. You have an object. You have a 20 newtons here and 35 newtons here. And we have an angle in the middle, 60 degrees. Watch this here. You don't have to make a diagram and look exactly like this. You have to have the right dimensions. So this 35, you can start it horizontally and then measure 60. That's okay? You don't have to do it at an angle, right? Start this one horizontally and then measure your 60 degrees and then work out your that. That's okay? Pick your own scale and work it out. I'll pass around to watch it. Pick your own scale and work it out. If you have no protractor, well. Right? Copy down the example and draw the horizontal quickly. Wait. And over this one, how I work it out. So take your time. You can work it out using cosine. A non-right angle, right? Cosine for non-right angle, right? E squared plus b squared. 2e minus 2 times c. Right, so as I said, your sketch might look like this, right? It might look like that in the end, right? And the angle here is 60. Right? It will not be like a rectangle like the others. This sketch might end up looking like this. What's a good scale that we use? What's a good scale? 1 centimeter is what? 5? Okay, that's something good. 1 centimeter is 5 newtons. Then I'll do it in 2 minutes there. Online if you get message your answer. Just looks. All right, so if you do it properly, here's 7 newtons, sorry, 7 centimeters. Then you measure up your little 60, right? And next one will be what? 4 centimeters. Right? Then you complete your parallelogram, right? And your resultant forces here. Right? Your resultant forces here. Right? Do I know the value? I don't know the value. I'm a calculator, right? I don't have I didn't do this scale diagram. So that'll be 7 squared plus 4 squared minus. How much is it again? 60? Right, I have approximately 9.6. 9.7, I'm taking that. Right? So the exact value for the resultant force is 9.64. Right? So on average, when you multiply that by 5, that should be about 48 Newton. Right? So I'll take anything from 46 to 50. Okay? Anything from 46 to 50, right? Okay with that? So that's the way you find resultant force. Okay? And once you do this in the direction of the forces, the diagonal is always the resultant force and the direction. Right. Or there's just one thing I did not mention. Ideally, this is only the magnitude, right? But remember, forces are what? A vector quantity. So you can't give them magnitude alone. You have to also give them direction. So what you can do is take a protractor and measure that angle. For each one of them, right? Take a protractor, measure this angle, and write it here. Okay? So you're giving them magnitude and direction. Are you okay with that? So you're giving them the magnitude of this line and the direction by giving them the angle. That's okay? So take a protractor and measure all these angles here. Right? And just include that with your answer. Right? Any questions online? Right? So you're okay with finding the magnitude, right? Keshav? Right, Keelan, I like that, right? I like how you said 30 degrees, probably 7 Newton. So that could work. Right, but if you draw the alpha on the diagram, they know what direction it is. That's very good, Keelan. Okay, chat Salim, all okay? Arisa Yedesel. Arisa, nice. Open on your phone, Arisa. Any questions here, Olivia? Nathan's, all okay? What's all again? Huh? Oh, we get 3 Nathans there, we? 1, 2, 3. Whatever the Nathan in front of. That 3 Nathans in a row there. Be there, you gotta move from there. Agreed? Yeah. How much else for the angle? 20. Okay. Chilan, check back the angle there, right? And when you keep resolving forces, right? Continue with forces and we're moving on to something called moment of a force. All right. So next heading, moment of a force, right? So suppose I have this here, right? Wait. Suppose I have this here. And I apply a force, right? Here is fixed, here cannot move, right? And I apply a force here, which is, right? I apply a force here. What would happen to this object? To move out. Down, right? So it will kind of turn, right? And if I apply a larger force, it will turn a little bit more. Okay? And based on where I apply that force, I can change the turning effect. All right, so watch this here. If I was to come sit. I'm gonna make you stand YouTube. And really one is no. I know in our life. Of course, it live. You think anything on this? Right. Watch this here. So apply a force here. Just apply a force. Right. Apply the same force here. So it's not moving as much, eh? Apply the same force here. Apply the same force here. Apply the same force here. Apply it. Right? So you all recognize, right? As we apply the same force closer to this fixed point here, the turning effect is smaller. Right? And that gives you an idea of what are the two things that control the turning effect. And then you can tell me what the two things are. Right? Number one is the force. What's the next thing? The force, the distance of the force from the pivot. That's okay? So those are the two quantities that control the turning effect of a force. That's okay? So a force can either cause this to turn how? What's that? Clockwise or anti-clockwise. So you have two types of moments. Clockwise moments and anti-clockwise moments. You okay with that? Nice. So that just a little introduction into what is the moment of a force, right? So head up moment of a force. What would you be on? Thanks, alignment. Right head up moment of a force, right? Right. So when I share the handouts on the group, which everybody in there knows, I can share it. It's up to you to print it, or you can keep writing and you can print and write on it, or you can keep taking the notes, right? Right. So what's the moment of a force? As I was saying, if I give you an object, I'll do the same example, and here's the pivot. Right? That point there is your pivot. Then the distance T between the force and the pivot, that represents the moment of a force. Right? So it's the product of the force by, right? And I'll give you a formal definition. Copy this down. And I'll give you a formal definition. That's not right. Force multiplied by, right? I'm using this symbol, perpendicular distance from pivot. Right? Just catch that quick. Catch that quick. Copy down. I'll give you a little, right? Right. Yeah, I'm not form of 35. I don't know what I'm doing in the corner. To take a small definition, the moment of a force, the moment of a force, or the moment of a force, or its turning effect, the moment of a force or its turning effect is the product of the force, is the product of the force is the product of the force acting on the object and the perpendicular distance, product of the force acting on the object and underline the word perpendicular and the perpendicular distance from the pivot and the perpendicular distance from the pivot. Sorry. Yeah, next week. Right, underline the word perpendicular, right? One thing I left out here is the SI unit. Somebody can help me out? What's the SI unit here? Newton meter. Newton meter. Right? Newton meter. Right? Very good online. Who's up? Somebody actually sent me something online. They're excited. Ravi. Well done, Ravi. Rajiv, sorry. Rajiv. Well done, Rajiv. Right? So that is your moment, right? And the reason I made you underline the word perpendicular is because of this, right? What is small example here? What is here? I am applying a force here, and that force is 10 newtons, right? I'm not telling you where the pivot is, that's the ground. You have to figure out where the pivot is, right? And I'm giving you two distances. One distance here, let's call that 2 meters, and the next distance here, 3 meters. And my question is, what is the moment of the 10 Newton force? Right? We know it's force multiplied by perpendicular distance from the pivot. So quick question. If I were to apply a force here, where will the pivot be? At the point A or at the point B? Where will it pivot? At a particular object here, and I apply a force here, it should pivot right here at point B. That's okay? So it should pivot at the point B. So the question is, what is the perpendicular distance from the pivot? Is it the 3 newtons or is it is it the 3 meters or 2 meters? Which one? 3. You're saying that? This is the direction of the force perpendicular here. Are you okay with that? Peter? So perpendicular to this is this 3 meters. So the answer will be 10 multiplied by 3, which is 30 Newton. You okay with that? Okay. Jordan? You okay with us? So this distance is parallel to this, so I don't want that. I want the distance perpendicular to this force. That's okay? You sure? So that's why whenever you write the definition, don't just write force by distance. You have to write perpendicular distance from pivot. Okay? Force by distance is what we do. Or it's force by distance. Huh? Force by distance is something else. Energy. Right? Energy, right? Okay, copy it down. Copy down that example, and we want to take a look at a nice little simulation here to put together, right? Keshav, you okay with that? Right, good job, Keshav. Keep it, keep following. I can't go down. Ready? I want to copy down. I want to show you a little simulation that I'm going to use to explain moments and everything, right? Where is that simulation? What do you write yourself? Yeah. Right, while I'm waiting, what the hand now? We form, one. Online, use doing form coders do my favor and just someone message saying 4 please. Right there on the group. Right there on the on Zoom. Oh, lab book sale, yeah. Right, so I will tell you that. So, pretty cool, pretty good in 1 year. Lab book sales, I want to get it and I'm going to tell you what they did. All right. All right, take a look here, right? So what we have here is basically an introduction into something called principle and moments, right? So if I were to place an object, take a look here, right? If I were to place an object here, forget the readings, right? What does that mass do? It causes the plant to turn how? By a solar. Clockwise? Yes, sir. That's clockwise. A clock will turn like that, right? If you're watching it. Right? So that's clockwise. If I place the object here, it will cause it to turn how? Anti-clockwise. That's okay? Right? So this object here, right, could cause anti-clockwise movement or clockwise movement. So you can move it one. And this one no, but you can move where the object is. Right? Where do I put this 5 kilogram object so that I can balance it off? On the other side? Be exact, right? The exact spot that the one on the right is on, right? So if I place it here, it will balance off, right? Well, okay with that? Right. So there's a reason why that happens. All right. If you look here, can I write on this? Right, I'm gonna put some rulers here, some markings, right? If you look here, both objects have the same what? Same distance from the pivot. And they both have the same mass as well. That's okay? So let's be a little more exact, right? Let's I can draw something here. This is the mass. What is the force exerted by that mass called? What is the force exerted by that mass called? Yes, weight. Right? That's called weight, right? That's what we did last week. So the weight of this 5 kilogram is how much? 50, because gravity is 10. So here's 50 newtons. And here's also Right? We'll start doing some past papers on this as well, right? Right. So they both have the same weight, 50 newtons, right? But Dominic, they also have something in common. What it is? Anybody? They also have something in common. Right? Because you said to particular distance, but what else? The distance here 2 meters. And the distance here is 2 meters. What else do they have in common? Same, something else. Yeah, same thing, but something else. What else they have in common? Hint on the board. Same weight, same mass, yeah, but you see it already. The same distance. Something else. It's on the board. Yeah. Same moment. And if I were to find the moment on the right side, and that'll be 100, multiply them, right? And if I find the moment on the left side, right? And the best I can do that. Right? You all recognize that they are the same? Yeah. So that brings us to something called the principle of moments. Once the clockwise moment equal to the anti-clockwise moment, the object will be balanced. Okay with that? So that's what we, right? So that's what we're going to take a look at, right? Since you only set simulation, right? Always remember, once the clockwise equal to the anti-clockwise, the object will be in equilibrium, right? Okay with that, Ethan? So when the movement on the right equal to the movement on the left, the object will be in equilibrium. So I'm gonna just change it a little bit, right? I'm moving this. I want to move the right. I want to do what I pick up this, right? I want to move this. Right. But and I want to balance it off, right? But I want to use the trash can. Exactly, Elon, where should that trash can go? I want to balance it off. Trash can is 10 kilograms. Righty? Why? Right, so you want to make sure the movement is the same, right? Work it out and make sure. 10 by 1 is 10, well, 100 by 1 is 100. And then 50 by 2 is also 100. So are the movement the same? Are the movement the same? Yeah. That's why it is level, right? Let me show you the level. Are you okay with that? Right? Let me make it a little more complicated. Slightly more complicated. Tell me where to put that. I want to balance the red, sorry, the what's called that? The extinguishers with the dustbin. Where do I put them? How you're allowed to move it around. Anybody can move it around actually. Online, take out it. Where do I put the red and where do I put the trash can so that it's balanced? Think about it. If you think you have it, I'll bring your mouse here. Very good. Right? It has plenty options. But that's one of the options, right? What's the movement on the right side? What's the movement on the right side? 100, right? Because it is this here, which is 100, multiplied by the distance here, which is 1. So that is 100 Newton meter. What about the left side? The left side is 50 by, how far is this? 0.5, 1.5, right? And then if I add this one, that will be 50 by 1.5, 1.3 over 2. And if you add it up, you'll end up with 100 Newton meter. Okay? So this here is called the principle of moment, right? So your homework, I want an example of principle of moments and write down the law for homework. All right? What is the principle of moments? And I want one example showing it. Write it down so you don't forget it. All right? That's the homework. That is your homework there. And next day we'll continue right into this, right? So we'll start back with a simulation and do some calculation. An example, you can show me the moment. What is the definition of the